All right, so I did get a request this morning to go over the K versus T homework and the concentration versus time homework. So we'll start with the concentration versus time homework because that's a bit more involved. Now, to put some framework in here, two things we try to do in any type of course is to teach you the theory and then teach you the application. And this homework here is meant to drive you towards the application. So pedagogically, what we're trying to do here is do two things. One, let you see how the theory gets applied, and two, kind of break you out of the mindset. Sorry, break you out of the mindset of assuming that this is all kind of being done like is a hypothetical isolated scenario. So when we talked, if you look at the notes, it talks about zero first and second order equations, and it talks second order reactions, and it talks about the solutions to these. So to recap, zero first and second order reactions. Take terms of concentration versus time. For zero order, it's going to look like this. For first order, it's an exponential, but we can linearize it to be natural log of A equals natural log of the starting concentration minus KT. And for the second order, I tell students don't even bother to memorize the function versus time, memorize the linear form because this is the far more useful form. So this is provable. We don't require calculus for this course, which is why we don't prove it. But these are, all three of these are provable. Now, the thing is that these can serve as hypotheses. So let's say we hypothesized a reaction is zero order. Well, if it is zero order and we look at the concentration versus time, it should be linear. And the natural log of concentration versus time and whatever concentration time shouldn't be linear, because if we take the natural log of concentration here, we get a weird function. So if it's a zero order, this plot will give a straight line. If it's a first order, the natural log of concentration versus time will give a straight line. Oops, sorry, I'm going in the wrong directions. Whereas concentration versus time and whenever concentration time will not be linear, because this is actually what it looks like, and if you try to plot this as a straight line, you get a decaying exponential. Now for the second order, similar reasoning. If it's a second order, we hypothesize it's a second order, then if we plot 1 over concentration versus time, we should get a straight line, whereas natural log of concentration and concentration versus time won't give you a straight line. So the thing is that these are three testable hypotheses, but when we acquire the data experimentally, what we actually measure is just concentration versus time. So experimentally, that's all you get. Now, if you look at the graph, if it's zero order, it'll look like a straight line. If it's set first order and second order, it'll start looking less and less linear. But this is assuming it has strong first order and strong second order behavior. That depends on the magnitude of K. So we need a good way of taking this data and determining if it's zero first or second order. And so that's what the homework is saying, is that if we're given concentration versus time, which is what we're actually going to measure in the lab, and we plot the data, how would we figure out if it's a zero first or second order reaction? So I'm going to bring up the homework, and I'm going to go to data set 2. So to figure out if it's zero first or second order, looking at concentration versus time, what we had to do was we had to look at these three plots. Concentration versus time, 1 over concentration versus time, and natural log concentration versus time. And to generate these plots, we're literally just going to manipulate the data we have. So we're going to use the concentration versus time data, and we're going to convert it to these through two other forms. So it's just mathematically manipulating the data. It'd be no different than if you just took a unit conversion. Let's say it was a molarity, you want to convert to millimolarity. It's kind of the same thing. So I'm going to go to the desktop, and we need natural log of A versus time, and we need 1 over A versus time. And from these, we're going to generate the three plots. Mercifully, this was not a zero order reaction. And quickly what you can see with this one is that it's clearly not linear. So it's obviously not a zero order reaction. So now I got a natural log of concentration versus time. I'm just going to generate it by looking at that plot. And 1 over A versus time. So these are the 3 plots from before, and each of them are a hypothesis. Come on, let me manipulate the data. There we go. This computer's a little slow. So what we're doing by generating this plot is we're creating 3 hypotheses. Hypothesis 1, concentration versus time, is that it's zero order. Natural log versus concentration versus time, this is a second hypothesis that it's first order, and concentration versus time, that's second order, whatever concentration versus time. So these are 3 testable hypotheses, and they work on an if and only if statement. So if it is a zero order reaction, if and only if it's zero order reaction, will concentration versus time be linear? If and only if it's a first order reaction, will natural log of concentration versus time be linear? And if and only if 1 over concentration versus time, if and only if the reaction's second order, will 1 over concentration versus time be linear? There is no conceivable scenario where we will get a situation where a reaction can be zero first or second order with regards to the same reagent. There's no other way we can generate these linear plots. So what we do is we look at the data and we say, okay, which of these plots are linear? Well, if we look at 1 over concentration versus time, this clearly isn't linear. You can see where the data kind of curves. So the hypothesis that it's second order must be wrong because 1 over concentration versus time isn't a straight line. Now, if we look at natural log of concentration versus time, that's a pretty straight line, r squared 0.9994. So that supports the hypothesis that it's a first order reaction. And 1 over concentration versus time, it's got a tiny r squared. It's really apparent here that this is not a zero order reaction. So the only hypothesis that survives this analysis is that the natural log of concentration versus time is linear, therefore it must be a first order reaction. So for data set 2, it is a first order reaction. So that's the first step of that homework, is that you have to figure out what the order is. And all 13 sets of data separately. I'm not familiar with all 13 sets of data. If you mean the data points, you can't take them individually. You have to use all the data points to generate these lines. So you can't use a single point. You can't use a single time concentration data to figure any of this out. You have to use all of it. Because what we're looking at is concentration versus time. The graphical analysis involves all the data points. So once we've figured out what our plot is, in this case it's a first order reaction, now we look at what the model says. So the model says that for a first order reaction, natural log of concentration is the natural log of starting concentration minus kT. So this tells us that if we use y as the natural log of concentration, x as time, the slope here is equal to the natural log of the starting concentration. And the slope here is equal to the negative of the rate constant. So if I go back to the data sets, just a minute. My slope here is minus 0.02, and my y-intercept b is 0.9152. So my slope here is equal to negative k, so k here is 0.02, and you got to go to 3 sig figs, so 0.0200. For our y-intercept is the natural log of the starting concentration. So our starting concentration is E to the y-intercept. In this case, 2.50. And that kind of makes sense. So if you look at the actual data, this is a nice thing about being given concentration versus time. The starting concentration was 2.49. This is in pretty good agreement. So for all 5 data sets, you have to take all the data and do the 3 plots and figure out which plot is the straightest. That will tell you the order. Then based on the order, you know what model to use in order to extract out the kinetic data, which is the starting concentration and the rate constant K, with the rate constant K being the more useful information. And that's really all you do for that homework set. Now, if you looked at the homework, there were 2 other homework sets that were concentration versus time. One gave you just a single plot and said, what's the order, what's the rate constant, what's the starting concentration. So all that's doing is seeing that if I give you a single graph, can you figure out what the order is and what the kinetic parameters are. The next homework set up in terms of difficulty was the one where it gave you the 3 plots and said, okay, what's the order, what's K, what's the starting concentration. In that case, the data was already processed for you to the 3 plots, so you had to figure out which one was correct. But all 3 of those plots were the exact same data, just in different formats. One was concentration versus time, which is what would have been measured. One was natural log of concentration versus time, which you just would have manipulated the data. And then 1 over concentration versus time, the same thing we did here. The only thing you're doing differently for this homework is now you're generating those plots yourself. So you're generating the 3 plots that you did for the homework, and then going through figuring out which plot actually best describes your data, and then use the model to figure out what the different terms are. So that's concentration versus time. And I've got the chat up in case you want to ask questions, but there's about a minute lag. So I'm going to start moving on to the exponential stuff. But if you have a question, we can definitely come back to it. So for rate constant K versus temperature, again, experimentally what we measure in the lab is temperature, and we calculate the rate constant K, and we need to find out the activation barrier. So to do this, we generate an Arrhenius plot. So K equals the pre-exponential, and unfortunately we have to use an A, it's just what we have, e to the minus EA over RT. And if we rearrange this algebraically, we'll get the natural log of K equals the natural log of the pre-exponential minus EA over R times 1 over temperature. So y here is the natural log of K, and x here is going to be 1 over the temperature in Kelvin. So we're going to have to do something similar where we need to convert our data, what we measured, into what we need to generate the plot. So all we do is we take our starting temperature, convert it to Kelvin, and then take 1 over that to get our x values. And to figure out our y values, we just take the natural log of whatever our measured rate constant is. Now, this is a hypothesis that if true, we should get a straight line with regard to ln K over temperature. And for these, we're only going to stick to cases where it does work. There's definitely exceptions where it doesn't. That's a higher level kinetics course. So we're going to get some fit y equals mx plus b. The slope by the theory is minus EA over R. So EA here is just minus R times the numerical value of the slope. B equals the natural log of the pre-exponential. So the pre-exponential is just E to the y-intercept. So I'm going to go to the K versus temperature data now. And I'll work case 3. So we need 1 over temperature, and we need the natural log of K. And I get it, you don't know what K is. That's on me. And then we need to insert our plot. So here I get my slope is minus 6721, and my y-intercept here is 6.6587. Now, a point of confusion I sometimes see with the Euretis plots is students are trying to equate this with the first order kinetic model. This is not concentration versus time. You do not see concentration or time anywhere in the data sets. But it's that false equivalency that there's a natural log in one model, therefore they're the same model. This is a different model. The first order concentration model says that the natural log of the concentration, so A in brackets, is the natural log of the starting concentration minus KT. These are not the same formulas. They both contain a natural log and an exponential, depending on whether you're using the linear or exponential form, but they come from different places. This is the solution to a first order reaction equation, rate equation, as a function of time. This is the Arrhenius relationship from transition state theory, which is the connection between K and temperature. So don't equate the two. They are not the same because they both contain natural log. Natural log is just an operator. It's a function. These are different theories backing up why this should be a straight line. So now if I take my data that I've processed, bring it back to the desktop, I know that my slope is minus EA over R, so I can solve that and get that the EA here is the negative of R, 0.008314, times the slope M. And I know that B equals the ln of the pre-exponential, so the pre-exponential is just e to the y-intercept. And we're going to do 3 sig figs here. So that'll give us 780 and also 56.0. And this is reasonable for this EA. Particularly the examples I worked, 25 to 150 is a reasonable range. There is no reasonable range for A. I just keep it in a range where you don't have to enter exponentials into WebAssign. So that's it. That's all you ever do for EA barriers. EA, you don't have to plot K versus temperature and 1 over K versus temperature because it's not a meaningful thing. Again, it's trying to make the equivalency between two very unrelated things in terms of analysis. So for graphical analysis, we can look at orders, or we can look at graphical for EA. For the orders, you need to plot the 0, first, and second order forms. So that's going to be A versus time, ln of A versus time, and 1 over A versus time. For the graphical EA, what we need to plot is 1 over temperature, or I'm sorry, ln of K versus 1 over temperature. So for the graphical orders, there are 3 plots we have to generate. And once we generate these plots, we determine the order. So whichever plot fits the best, that will tell you which order is which. If A versus time is straight, it's a 0 order. If now ln of A versus time is straight, first order. If it's 1 over A versus time is straight, that's a second order. Once we know the order, we're going to use the models to get K and the starting concentration. And this K here, that's where the graphical analysis comes in. So you would measure K at a whole bunch of temperatures and use those temperatures to figure out what the activation barrier is. Once we get this ln of K versus time, we'll use the model to get the pre-exponential and, more importantly, the activation barrier. The pre-exponential A is important when it comes to reactor calculations. The EA is the more useful one because it's globally useful. A is a highly depends on the reactor you're using, the reaction conditions you're working with. EA should be independent for that reaction, assuming you're using the same reagents and catalysts. Now, we definitely don't do, particularly this level, just because it's just too much. Making you find K at a whole bunch of different temperatures based on kinetic data and then tweezing out EA. That's something that would be done in the lab for a seated course just because we have the ability to control that. But in terms of classroom, it's just too much theory to absorb. But yeah, those are the two Excel homeworks. Let's see if I can bring up the homework to show you the parallel. Origin concentration, I think that's method of initial rates. Yep. Sorry, I misspoke. You don't have a homework that, that's odd. I thought I had one like that. Hmm. Who knew? But yeah, you have one homework that starts out like, actually, it's not like, it is this one here, where you're given the plots and asked to extract out the kinetic information. That's basically all you're doing with the Excel sheets. You're generating these various plots. You got whatever concentration versus time, concentration versus time. All right, so that's it for questions people sent me in advance. Are there any questions out there from those of you watching the chat? Good morning, Dia. How are you? It shouldn't really matter if it's JPEG, PNG, or PDF. My computer can read all of them, and that's more of an honesty test more than anything else. Um, we have had issues in the past where like students have gotten people to like basically cheat for them. So if there's anything weird, we can go back and verify that it's actually you that did it. I'm doing well. Glad it's like technically my Friday. It's Thursday. But it's nice. I usually use my Fridays to go run errands, do some. I go climbing on Fridays. Yeah, you're welcome. Actually, you would. So yeah, this lag is really obnoxious, but it's that compromise between like latency, how good it looks, and how quickly I can talk back to you. If you don't mind the video being completely grainy and impossible to see, I can talk to you in real time. But you need to convert to Kelvin. So if you ever see an R, T is in Kelvin. So the instant you see the ideal gas constant, it's automatically in Kelvin. That just kind of needs to be your knee-jerk reaction, or at least like get developed into that knee-jerk reaction of saying that, oh, ideal gas constant, automatically in Kelvin. And the way you can kind of justify this, let's say we took the measurement at 0 degrees C, 1 over temperature would be infinite, which we know we can't plot. So that's kind of the tip off here that we need to be in Kelvin. It's impossible to get to absolute 0. Well, concentrations can't be negative. So any starting concentration has to be greater than 0. It's impossible to have a negative concentration. You're not taking the natural log of B. You're taking the exponential of B. Because we have the relationship that B equals the natural log of the starting concentration. So to undo this natural log, we have to take the exponential of both sides. And that exponential will cancel it out. But conceptually, it doesn't make any sense to get a negative starting concentration. That's impossible. You can't have negative moles of something in solution. You're welcome. As a reminder, you do have your exam this week. I mean, I know most of you saw it, but exam is open tomorrow and opens and is open through Sunday, like all the exams. There was a typo in an earlier announcement, I think. But I'm definitely going to try to keep it consistent for you in terms of the exams. Always on the weekend. Always try to give you about 3 days to take the exam, just in case you've got work schedules or something that you need to work around. The only exception here is the final. The final exam has to be in person unless you can't physically make it. I know we've got students in here in Ohio and Florida. If you can't make it, send me an email just so I have the documentation. And there will be an online version of the exam you can take, and we'll talk about those details privately. But generally speaking, though, it would be preferable if you took the exam in person. And for those of you carrying on into the fall, we're actually looking to go to in-person proctored exams in the fall with the e-learning testing center. E-learning testing center, you schedule time, you show up, you take your exam. Basically, it's remote proctoring. But if you are carrying on into the fall, yes, we are going to start switching more and more back to in-person exams. I physically won't be there at the ELTC, but you will get to take a physical exam. You will have more than just like what you're doing right now. Sorry, there's a little scratchy today. You're welcome, Tracy. How are you? I'm sorry, Professor Cheatham. Actually, the best live streams are when I have like organic and Chem 1 because I watch both sides getting really freaked out in the chat menus. Like, I don't remember us ever covering like quantum numbers and like, is this going to be on the exam? And then the other exam's like, are we supposed to know how to name organic compounds? This seems really advanced. It's like, it's just so great to kind of watch that duke out in the chat menu. Especially if I have students who've had me for a while. Senior Professor Cheatham, I'm sorry. Congratulations. I get some weird people that show up in these chats, by the way. Hey, it's fun. A lot of former students, because they went to my channel enough times, actually like see me in their recommendations. And apparently, I'm big in India and Bulgaria. I'm actually an assistant professor now. I got my faculty rank in the spring, so I'm no longer a lecturer steward. I'm assistant professor steward. Yeah, thank you. It seemed like a better use of office hours than just kind of sitting there and like hoping someone would chat in. If you definitely go back, there's a lot of videos of me playing the banjo too, because I mean, if students don't have questions, they don't have questions, and that's kind of my view on this. Like, this is an office hour. Like, if you don't need it, don't use it. I'm not going to force you to show up to office hours. I'm not going to force you to do anything. Like, it's your course, your tuition dollars. Use it as you want. All right. See you later, Senior Professor Cheatham. Yeah, you're welcome. And if you've got more questions, feel free to ask them. Like, this is your time. Um, Again, I don't see a point to doing lectures during these. These are office hours. These aren't lectures. But if you have questions, please feel free to reach out. Like, I want you to succeed in this course. But again, like as I said to Professor Cheatham, like there are a lot of resources. So like, if you don't need this resource, don't use it. There's the videos. There's a whole bunch of stuff. My view of teaching is that you should fail a course because you genuinely don't understand the material or you're just genuinely not trying. But there's a theory of teaching that says that there are intrinsic and extrinsic reasons why students fail a course. And as an instructor, my job is to minimize the number of extrinsic reasons you can't pass a course. So extrinsic may be that it's not a format you understand, you don't have enough examples, you don't have resource, things that I control. Now, there are intrinsic and extrinsic reasons that are beyond my control. Some students, like family crisis, they're having to work like two jobs, like I can't control that. Or there's internal motivation, like some just don't try. I can't control that, but I can definitely reduce any other barriers for you. Because the other thing is that we want to make I say we I personally want to make sure like you go on to the next course prepared. Um, and that's sometimes hard to communicate. Is like, yeah, I tend to run y'all really hard sometimes. The point is that I want you to be successful in higher courses. First course I took in chemical engineering at NC State was Chemie 205. It is a notoriously brutal course, but they tell all the students like if you can pass Chemie 205, you can do chemical engineering. And it was a pretty accurate statement. Like if you had the mental fortitude to deal with that course, really all of other chemical engineering was just taking that course and making the details more complicated, but the concepts didn't really get that much different. With Chem 1 and Chem 2, my goal is usually to get students really prepared for their higher courses, like get you on a good footing with the theory, get you on a good footing with the study habits and the resources that work best for you. They are cumulative, but not in the sense that like there's going to be questions from test 1 on test 2. The concepts are cumulative. Um, so the amount of cumulative kind of varies from exam to exam. Definitely for exam 2, I would say you're not going to see much from the first exam. But I'm trying to think about what would be from the first exam. Yeah, the cumulative is just kind of more of a legal disclaimer, but it's not like you're going to have questions on osmotic pressure for test 2. Like that's not going to show up. You're not going to need to do delta 2 equals KIM. But and a good example of this is like converting mass to moles. You learn that in Chem 1. You still need to know how to do that for these exams. Like you still need to know like basic. You saw this with the pressure dependent gases. You had to know what the ideal gas law was. That's a Chem 1 concept. So they're cumulative in the sense that you still kind of need to know basic concepts. We're not going to go over them. But not cumulative in the sense that I'm literally just going to pull questions from test 1 and put them on test 2, 3, and 4. Now, the final does actually have questions like specific to test 1, test 2, test 3, test 4, and the new material. But that's because the cumulative has to be that way. But again, cumulative here means that basic concepts can be carried over. But you would have seen those in the problems you were working. So if there's a concept that dials back to test 1, you would have seen that when you were going through the notes. When we did the next test on equilibrium, it's going to kind of assume that you remember how to calculate molarity, which you should know from the test 1 material where you were having to figure out molarity, calculate molarity in order to calculate osmotic pressure and things like that. That you should already know how to do. So we're not going to go over how to calculate molarity, but it is on there. Again, the final is the only one that specifically goes back and tests like subject area material from those tests. But there are a lot of overlapping concepts. Yeah, you're welcome. I had a student in my Chem 1 course one semester who, because Chem 1 in particular is very much a cumulative course. And it was great to hear him like blurt out after test series like, oh, it all connects because like people don't believe instructors. And don't get me wrong, I've met instructors who've straight up lied about things being cumulative in courses. I totally get why you don't trust us. But to have them blurred out, I was like, oh, it all connects. It's like, that really helped. Yes, so catalyst from reaction mechanisms. So let me, hopefully I got a copy of it somewhere quickly available. Let me download one of the practice packets. So we have products, reactants, intermediates, and catalysts. So overall reactions, let's say you have, we'll do the water example. So your products are at the end, your reactants are at the start. But each individual reaction mechanistic step has its own products and reactants. So the reason why when I ask you to find the catalyst or find the intermediates and I don't give you the overall reaction is because honestly it would make these problems stupid easy to do. So up here the catalyst always has to be written above the reaction arrow, and pretty much anything that doesn't show up in this reaction here is an intermediate. But that doesn't get you to think critically. So within each individual step of the mechanism there are products and reactants. The intermediates start as a product and finish their life as a reactant. So when we go to identify intermediates, we're looking for something we didn't start with and we end up using as a reactant further down the road. Catalysts are the reverse way. They started as a reactant and they finish as a product. Because the thing about catalysts is, for an ideal reaction, they're not consumed. So they're involved in the reaction, that's how they catalyze it, but when the reactions gone or finished, they go back to what they were. So for the intermediates, like this 2-HPT, it starts as a product, finishes a reaction. This 2-OPT starts as a product, finishes a reactant. The catalyst is going to be the other way. We're going to see it on the reactant side, and then we're going to see it on the product side. So here we see the platinum on the reactant side, and it finishes up on the product side. So the catalysts are just the reverse, follow the reverse behavior of intermediates. So I'll bring up one of the ones in the packets. So scheme 3 is a good example of this. So we make CH3BR-Mg, CH3, CH2, MgBr. So it's a product, and then we see it consumed as reactant. So that would make it an intermediate. And then we have MgBr2, which we see as a product, and then it's consumed as a reactant. CH3Br, we see it as a reactant only, so that means it would be a reactant in the overall reaction. And this CH3, CH2, CH3, we only ever see it as a product. We never see it as a reactant. Same thing's true of this Br2. We only ever see it as a product. But the magnesium here, if we look at it, it starts out on the left side, unlike the CH3, CH2, MgBr, and then it finishes up on the right side the last time we see it. So that would make it a catalyst. And same thing's true down here. So if we look at the R2N3, that's an intermediate because it's first a product, then a reactant. Fe2O3, first a product, then a reactant. The RU2NO3, product, then reactant. Fe2O3 is a reactant again. So the N2 only ever appears on the left side, so it's a reactant. The NO2 forms on the product side only, so it's a product. But if we look at the ruthenium, first it starts out on the left side, and then it finishes on the right side. So that would make it a catalyst. The Fe is the same way. It starts out on the left side as a reactant and finishes as a product. So this is what we mean when it acts as a catalyst. It gets involved with the reaction. It's a reactant. But when the reaction's said and done, when we produce this NO2, sorry, missed that iron there too, we get it back out. So the ruthenium isn't consumed during the reaction. It's first used and then it's put back. The iron's first used and then it's put back. All right, so if you have time to go over the orders from concentrations homework, that would be great too. Let's see here. Let me bring it up. So, quick question because I can answer this one. How do you know if a reaction is the rate limiting step? You don't. There is no way to look at a reaction and know inherently if it's rate limiting. There are things you can infer. Typically, anything that breaks a diatomic gas, so like oxygen or nitrogen, those contain multiple bonds, those are generally rate limiting. But even then, something like oxygen dissociating a platinum, that's actually spontaneous at room temperature, so it's probably not rate limiting. So there is no way to look at a reaction and say this is definitely the rate limiting step. There is a whole branch of catalysis that focuses exclusively on trying to figure out what the rate limiting steps are. So you would have to be told that information. All right, orders from concentrations homework. So this is just method of initial rate. So the orders for concentration is method of initial rate. And in this case, we're going to use the formula of the natural log of one run over another run equals the order of reactant A and the ratio of its concentrations between the runs plus the order of B Now the trick here is to find two reactions where the concentration of one reactant doesn't change. So if we go to the homework, we can work with this first problem here. So it tells you automatically it's orders 2 and 1. So we've got rate 1, 2, and 3. Concentration of A stays constant between run 1 and run 2. B, it stays constant between run 2 and run 3. So let's compare run 1 versus 2. And I'm going to look at my shoulder. So we have the run for run 1 is rate 0.0145. And run 2, 0.0255. And the concentration of A from run 1 is 0.589 for both. For B, 0.336, 0.600. So this is just 1. And the natural log of 1 is 0. So we get this relationship that the order on B is just the natural log of these two numbers. Okay, so the order on B is the natural log 0.0145 over 0.0255 divided by the natural log 0.336 by 0.000. So we can solve this algebraically just by picking two runs where one of the concentrations doesn't change. So if you do run 1 versus 2, since B's concentration is changing, that'll give you the parent order of B. And then I think if you compare 2 versus 3, that'll tweeze out the apparent order of A because the concentration of B isn't changing. This is just method of initial rates. Now, you don't necessarily have to do these combinations. You could do 1 and 3, especially if you know one of the orders already. But honestly, it's just a lot easier if you work with it with only one of the concentrations changing. I'm seeing that there's relief that you don't have to know what the rate limiting step is. Yeah, it's not straightforward. And it can change. This is when I talk about how those Arrhenius plots, ln to k versus 1 over temperature, you can suddenly see a change in the slope. The rate limiting step can change. The rate limiting step can change. So that early example with the hydrogen and platinum. At low temperatures, this is the rate limiting step because it's diffusion limited. So what's happening mechanistically is the hydrogen and the platinum are on the surface and they have to diffuse into each other to find each other. So at low temperature, diffusion is really slow. Yeah, you're welcome, Sophia. At high temperatures, this is actually the rate limiting step. Because now the hydrogen and the oxygen have so much energy, they don't want to be stuck on the surface. So even with temperature changes, you can shift what the RLS is for the given reaction. This is why we don't require it. Like, you would need to take a higher course where you would prove a lot of these relationships. You would prove, especially when you first time you prove Ellery-Riedel and Langmuir-Hinshelwood kinetic models, this begins to make a lot more sense why your rate limiting step can shift. But there's no way to tell. If I just gave you that reaction and said, what's the RLS? If you knew a lot about kinetics, you could argue a lot of answers. So we just don't bother with it. You can measure it. All right, so that's kind of the end of the live stream. Thanks, y'all, for showing up. It's actually enjoyable. Again, if you have questions, please feel free to email them. I will try to be in contact this weekend. That said, it is the weekend. You're going to have to give me time to respond. Do try to take the exam by Friday or Saturday. I'd already had one person say they need to take a Sunday. That's fine. The reason I say don't wait till Sunday, if there's issues, there's not much I can do for you like come Sunday afternoon. All right, good luck on your exam, and I will see y'all next week.